Hi folks, welcome back to Physics with Captain Rod. I'm making this one here to help you with Unit 2-2, 7, 9, 10, and 11. So let's chat about this. Number 7, it says a 7.8 gram bullet initially moving at a certain speed. So right there, we can start with, we know we're dealing with a bullet. We're given a mass and a velocity. Let's put a velocity vector in maybe. This bullet hits a tree. So here's kind of our picture of our tree here. Now this is before impact. Now they also say something about like the bullet penetrates into the tree. So draw a second picture. Right? And it probably, it might look more like this. So the bullet will have probably put some sort of hole in this tree. And this will be some distance here. Maybe we'll just put D here. So this is like a picture 1 and a picture 2, before and after. Here's a good example of where you can write out the work energy theorem, right? Which holds for all systems. Right? So the PE1 plus KE1, total mechanical energy of the bullet, state 1. PE2 plus KE2, total mechanical energy of the bullet, state 2. The work term will be for forces applying, or will be for external forces applied to that bullet. You'll notice that the bullet's got a very significant kinetic energy in picture 1, but not in picture 2. Right, so there had to be work done. So you also want a free body of the bullet while it was penetrating, when it was like in this region, still moving. And that free body, I'll go ahead and help you out with this one. Like here's the bullet. And it would be probably kind of deformed here. And no doubt there's going to be a fairly massive force this way on the bullet. Now this force will vary. There's no reason to think it's the same when the bullet's here versus here versus here. About all we can do here is just say some average force. I'll put a bar over it for average. Now the bullet has a weight to it, but the weight of a bullet is just not a significant force. Really crappy example, but imagine you hold your hand out. And then you take a pistol. And you shoot it through your hand. And you think about the force interaction. Is the weight of the bullet a relevant factor there? Ask yourself. And hopefully the answer to that is fairly obvious. Okay, I'm sorry about the crummy example, but I hope it makes the point. The weight of the bullet, not a factor in there. All right, that's going to blow through your hand, having nothing to do with the weight of the bullet, basically. Same thing here. The weight of the bullet and this force interaction between the tree are the weight of the bullet's basically insignificant. Now, this problem doesn't have anything to do with potential energies either. Even though I drew it lower, there was no, this is all a one-dimensional motion problem. The second picture is I just drew it down here because I had room. So there are no potential energies to worry about. Just datum it out. Just call that your datum. There's no potential energies. So, and when the bullet's at rest now, right here, your KE2 is 0, not moving yet. So you only have two terms, a KE1 and a work term. And the work term is going to be a force times a distance. And also keep in mind that during this picture here, the bullet's actually moving this way. So think about that in terms of the sign, S-I-G-N, on that work term. So that's enough in number 7. Let's chat about number 9. Okay, it says something about a base runner here. Let's just get rid of all this stuff. Okay, a base runner. That's a person running. Right, really crummy picture here, but good enough to kind of get us started here. They slide into second base, so they kind of dive maybe. And here they're sliding. And then, maybe here's another picture of them stopped. Let's put like a 1 and a 2. And I'm sorry about these super crummy pictures. Okay, but again, it's your homework. Make your pictures Picasso perfect. So, let's see here. The coefficient of friction is 0.7. So if we think about when they're sliding, the frictional force is this way. And they're going to be supported by the ground, so there's a normal and a gravitational force. You're going to use that coefficient of friction to find this. So this will now be a known value in this problem. All right, you're going to start by getting the normal. Hopefully it's obvious what it is, and then calculate this. All right, then write out a work energy theorem for this. PE1 plus KE1 plus work equals PE2 plus KE2. This problem really isn't about gravitational potential energies. Although it's true, we have a higher potential energy here than here. There's no distance given. This problem just isn't about that. You can leave that off with impunity. I don't think it'll affect your results. So you're going to ignore these. You're going to have a KE1 term with enough values given to calculate it. And then you're going to have a work term coming from this free body. And then when they're stopped, no kinetic energy. So that should be enough to get that one rolling. Again, I apologize for my super crummy pictures. All right, let's talk 10. Okay, a bullet. 10 is basically the same as the previous one. I think it was 7. Bullet given, speed given, write out the work energy theorem for it. You won't have much trouble at number 10. It's basically the same as before. Number 11, there's a mass given. There's a velocity given. It says something like at point A, and then there's a kinetic energy. Mine says 8.5 joules. Yours will probably say something different at point B. Now, right away, the kinetic energy at B can be expressed 1/2 m velocity at B squared. And you're given the kinetic energy and the mass. So you can calculate the velocity at B, no problem. I'm sure that'll probably be relevant. And then the kinetic energy at A is just 1/2 mVA squared, right? And these are given values, just calculate them. Part C, so when it says, what is the total work done? Write out the work energy theorem for this, right? The PE1 plus, actually PEA plus KEA plus work equals potential energy B plus kinetic energy B. Just write that out. And take note that there aren't any potential energies in this problem. Just call these 0. And that should be enough to get that done. So, all right, enough on that one. I'm going to stop that and save it right there. Have a great day.